Okay. Guys, do you hear me? Okay. We're ready for the second talk of this day. And the talk is presented by Alessandro Papadopoulos, who works in the MDH University. And I'm very happy to, I'm the first one to announce you as a full professor, am I right? Am I correct?
Yes.
He became full professor yesterday.
Yeah.
So,
so drinks on you.
so congrats.
Thanks.
Well, it's yours.
Okay, thanks. So welcome everyone. So my name is Alessandro, and today I'm going to talk a bit about how to use control theory for the design of self-adaptive software systems. And I have this initial sort of warning that, of course, what I'm going to present is going to be biased towards what I'm doing, but there is a lot of people out there that is actually working on several other things using control theory, especially also in the self-adaptive software system domain. But with this, I will start and I will briefly introduce me. So I'm Alessandro, and I'm working at Meredale University, which is probably not the most well-known university in the world, but it's like located here in let me see. It's located here in Sweden. It's very close to Stockholm, and it's in a city that is called Västerås. That reminds kind of Game of Thrones thingies. And of course, if you Google, then it looks more or less like this. But then in practice, what happens? I mean, these are the pictures that I've taken. In Sweden, of course, it gets very cold, and especially during winter time, you get like a frozen lake in front of the university, and this is actually the entrance of the university. So I actually got my PhD here in Italy, in Politecnico di Milano, but I moved to Sweden, and I have to say that I really like living there. It's quite an exciting place to be. It's a very nice research environment, and we're working on several cool stuff, very close to several companies that are out there. I'm actually currently working also with ABB, that is a big company working with robots and industrial automation, for example. And it's very exciting because, I mean, you get the chance to really work on some concrete problems and sort of come up with some academic solutions. But at the university, I'm actually leading a research group together with Professor Nolte. So this slide is outdated now. So I became recently professor just yesterday while I was on the plane. So that was good. And we actually do a lot of research in different contexts. So the title of the group is Complex Real-Time Embedded Systems. So we are focusing very much on embedded systems, but over time we have been working more and more with distributed systems and stuff like that. So I will not spend so much time advertising myself. So let's dig into the details of what I want to talk about today. So today I want to focus on control theory. That is why it is highlighted there. But I will try to give some motivation right now. So we are living nowadays in a very interconnected world with your smartwatch connected to your smart refrigerator and your mobile phone, and everything is kind of connected to the cloud. And in the middle of the picture, we are also there. We are actually interacting with this type of systems. We have expectations. We are the ones sort of setting the demand that is the workload that is going into this type of systems. And the number of interconnected devices is growing quite significantly. So this is actually a prediction that was done by Cisco several years ago. And they were predicting something around 50 billion devices connected in 2020. Now we are in 2022. So I was looking for some more updated figures. And I mean, this is, I think, Ericsson that had an estimate of 5.7 more mobile users than what happened in 2018. And in general, I mean, these trends are growing significantly, and we have to find ways to handle things in a proper way. We cannot just like let it grow and then the complexity of the system is going to grow, and we are not going to be able to control the overall complexity that is emerging from this type of system. And I want to relate to a simple example. Let's say, I mean, this may have happened to several of you. So you after a very long day, you go back home, and then you sit with your partner, and you want to watch a Netflix show, and then this happens. And of course, you are unhappy because, I mean, you really wanted to watch the next episode, and your night is screwed. Now, this is not happening only with Netflix. This happens with Twitter and several other services. For example, just to give another example, like the Canadian immigration website went down during the 2016 elections, and then apparently several people, while Trump was elected, started connecting to the Canadian immigration website to get to know how to get to Canada, because they didn't want to stay in the US apparently. And it went down because it was not designed to scale for this type of systems, or for this type of workload. And this is okay because most of the time, this type of websites or services that you are accessing are kind of soft services. So if they go down, yeah, maybe your night is not okay. Maybe you cannot tweet your very clever thought. But then it's okay if they go down. But the problem is that we are going also towards autonomous vehicles, and we are looking into safety critical systems, and you don't want this to happen, right? And the car is going to be connected to the internet, and the car is endowed of like some sort of autonomy locally, but still this type of faults may happen, and they may happen for several different reasons. And one of the reasons for these things to happen is that the systems are growing in complexity, as I'm saying, and we have to tame such an emerging complexity in a structured way, okay? And I mean, the take-home message of my talk is really, if you have to tame it, try to tame it in a structured way, using a framework that is kind of well understood and well established, so that you can build on something that is kind of solid ground. And I report here, like, I think it's from 2010 or even earlier, 2011. This is the cover of Nature that was speaking about taming complexity. I think this paper really influenced my research over time. And it's about the mathematics of network control, and in general, the usage of mathematical models and solid methods for controlling and taming the emerging complexity of these interconnected systems. So I've been speaking a bit about control a few times now, but what is actually control? So how many of you have taken like a control theory class here? Sometimes it's called controlli automatici or fondamenti automatica or these type of things. How many of you? Raise your hand. Some of you. How many of you have understood why you were studying this? No one, or few of you. Actually, this is a big problem in my opinion, because several people, you sort of end up with like, you have like this differential equation, and you have to prove stability of the system, and it's not very appealing several times, right? I will try to change a bit this perspective today. I will try to give you some nice and cool examples of how you can actually use control, and I will give you, even if you haven't taken any course like that, I will give you some hints of what is control and try to sort of give a tutorial in this direction. And by the way, if you have questions, I'm happy to take them also during the talk. So please feel free to interrupt me, okay? No problem. So the term control has different meanings in different communities. So this is not my definition. It's actually from Carl-Johan Ostrom and Richard Murray from Caltech, and Ostrom is in Lund. And in general, this is the introduction of the book that they wrote. They define control, any algorithm that is based on some feedback mechanism that is controlling the behavior of an engineered systems. Okay, so it's very generic. It doesn't need to be like a physical system. It's not an inverted pendulum. It's not like a transfer function that you get from somewhere. It is any engineered system. It can be even a software system. Okay. And Carl-Johan is speaking several times about the control as being the hidden technology, because I mean, maybe you have not heard about control before, and maybe you don't realize how much spread the control is, but on a daily basis, you are actually using several different types of control systems, from the temperature you set in your climate control system all the way to when you are driving your car, and then you set a target speed that you want to follow, and then you have the adaptive cruise controller, to the ESP that is trying to control the stability of the asset of the car, and so on and so forth. I can go on with several different examples. And it's very widely used. It's very successful, but it has been around for several years, control engineered systems. But typically, people don't talk about it except when there is a big disaster that is happening. And I think, I mean, if some of you are working with computer security, one of the classical examples is the attack to Stuxnet. That was actually an attack to the control system of a power plant. Because if you can break the control system, then you can make huge damages. You can make a plant blow up, or a car driving in a crazy way, or whatever you want. So what is a control system from a conceptual perspective? You have a plant, you have something that you want to control, behavior that you want to control. You have some sensors that are actually giving you some information about the plant that you want to control. And you have some sort of intelligence. And this intelligence can be kind of in any form. It can be like reinforcement learning, it can be some mathematical function, it can be a heuristic, or you are the one designing the intelligence. And typically the intelligence is fed with some additional information like, okay, what are the objectives that you want to achieve? What are the things that you want to do with this plant? And some additional knowledge or models that you are introducing to the intelligence to take the decisions, because I mean, if you don't know anything about what you want to control, you can do very little. And then typically the intelligence is giving some commands to some actuators that are controlling the actual behavior. And typically there is also an environment that is kind of surrounding the sensors, actuators, and plant. Okay, and the environment is going to change also and affect how the plant is behaving, and maybe some actions that you took like 1 hour ago are not good enough nowadays. Like, for example, if you're driving a car and you set a target speed of 50 kilometers per hour, then you might need right now like a certain amount of power, but then maybe there is some wind, and then the same amount of power will not lead to a specific, to 50 kilometers per hour. So you might need to have a bit more power or a bit less. Now, curiously enough, this is like the classical view of people that are doing, for example, agent-based systems or artificial intelligence and stuff like this. But so it looks very similar to an agent in AI. But in practice, if you just rearrange the same blocks in a different way, that's exactly the same view as a control system. And typically in control, we call this a block diagram because there are some blocks that are interconnected, and then you provide some targets and objectives to the intelligence. The intelligence is embedding some knowledge that I didn't report here of the system, and then somehow you are controlling the behavior through something that is called a feedback loop. And the feedback loop is practically given by this line that is going back from the plant to the intelligence. Okay, so whenever we speak about the feedback loop, we're actually saying there are some sensors measuring some quantities, and we are actually feeding the intelligence with this information. Good. So some examples, as I was saying, well, temperature controller, you can have like the heater or a cooler in a room. Then the environment can be like the external temperature or how many people there are in the room. For example, in this room now we're like, I don't know, 50, 100 people. And then everybody is like emitting some heat, right? And then we are heating the room. So if the objective is to heat the room and then it's very cold outside, then you're actually helping the control system to heat the room. So the idea is that this environment is something that is not possible to control. It happens, but then you have to be able to measure what is happening, and then the control logic should sort of decide how to act on the actual heater or actuator. And the same goes if you have a car and several other application domains. So I will not go through all these different application domains that are like the classical application domains that you find in a control class. What I'm interested in is, what about computing systems? So in physical objects, you have physics and physical model you study, like a lot of courses on physics, modeling, I don't know, electrical machines, electrical circuits, and whatnot. And typically you end up with a lot of equations that are ending up in the end into something that looks like this, and that's why you are taught in control courses that you have a system that looks like a differential equation in state space form, and you have a mathematical model. And then based on this mathematical model, you can sort of design some controllers. But the problem is, what about computing systems? There is no physics, right? There is no, I don't know, Newton's law in computing systems. Not really. So I like to sort of mention this or quote this by Linus Torvalds. That is, computer science has a lot in common with physics, actually, but they are different at the fundamental level. And then in practical terms, the big difference is that while in physics you get what you get from nature, in the computer science domain, you are the one designing what you are actually controlling, right? So you are the designer of the operating system or the software system or whatever. And then he says that within the boundaries of the computer, you are kind of God in a small scale. So it is true, and I want to stress that within the boundaries of the computers, you are God in a small scale. Whenever you start adding communication and you start adding some other layers and you consider an interconnected system, then it becomes a bit more tricky. But within the boundaries of the computer, you are God. You can create whatever physics you want, right? What is the physics? Well, I mean, I will go very quickly here. The more you move away from the hardware, so if you are at the hardware level, you have maybe the electronics and you have some knowledge of or models that you can use for modeling what is happening. But then the higher you go in the level of abstraction, or the more you move away from the actual physical architecture, then the more it's going to be a bit more complicated. All the way up to, for example, the cloud. And cloud computing is kind of up there, and you don't really know how it works, and it's a bit more complicated. And I want to give a historical perspective also about this. I mean, I'm still in this motivating phase. I will bore you to death with this. But I mean, I'm half Greek, so I like having Greek letters in my papers and presentations. So this is like a parallel that I think is motivating why control and computer science have not talked too much over the years. And I mean, I have two timelines here. So the control theory timeline, so from top to bottom, and computer science from top to bottom. I want to start with the computer science. I mean, let's say that it originated more or less in the 30s of the 1900s with the Gödel's incompleteness theorem, and then there were several fundamental contributions all the way to the Turing machine, and then the Unix operating system was created, and blah, blah, blah. So what really matters is not what I'm putting here. It's more like the years. What happens with control theory is that it was born more or less at the same time. But the problem is that when people were designing computer systems, they didn't have this type of tools. So it was not in their toolbox. So they had to invent some smart ways to, for example, design an operating system or to design some fundamental functionalities that, at the end of the day, if you think back, they could be designed as control systems, but they were not. And right now, we build so many layers on top of each other that it's very difficult to say, well, let's rethink from scratch how the operating system, the kernel of the operating system is designed, because it's very difficult. Even though it's modular, even though there are so many layers and everything is so much interconnected. I don't know if you have ever tried to touch how the scheduler of Linux works. It's a nightmare. You have to know what you're doing. So the question that is motivating the whole research that I'm presenting is, can we make the two parallel lives meet? So can we sort of at least try to redesign a bit some of the functionalities? And there are several books that have been published over the years. I think one of the most impactful book is the one on the left. That is like this feedback control of computing systems that was by Hellerstein, Yao, and Pagerank, and Tilbury as well. So they actually did something that I'm trying also to do more or less today. That is how to use some classical control mechanisms in computing systems. I think they did it from a very computer science perspective, so they didn't really think through some of the things that they mentioned in the book, but I think it's very interesting to read. And there are some other books that I can suggest. So let's start with the crash course on digital control theory. And don't worry if you don't know anything about this. I will try to sort of not assume anything, but I will try to give you an understanding of what it is, because I'm going to use some of these ideas and concepts. So I'm going to speak only about discrete time dynamics, meaning that there are no differential equations or stuff like that, but there are some difference equations, which are the equivalent of differential equations, but in discrete time. And I'm speaking about discrete time because computing systems, they live in a discrete domain, meaning that there is a clock in your computer that is sort of setting the time at discrete time instance, okay? And this is fundamental. So mathematically, what happens is that we have something that is x, that is kind of the state, that is measuring more or less everything that is relevant for a specific application. And it evolves over time instances that are indicated with k. And typically, this quantity evolves according to the previous values of x and some external input that I call with u. Okay, so we can say that the next value of x is a generic function of x and u. And now I'm not telling you much more than what you have learned in the control course. And typically, we are using, or people are using, linear systems that are very common in most of the papers that you can read in the area. Because these type of systems are, I mean, maybe they're not very representative of what is out there, but they are extremely useful. Because, I mean, they are simple enough, and then they can be sort of adapted at runtime. I mean, you can learn this type of models at runtime and then adjust what is happening. Some examples of what is a discrete time system. So this is a stupid example, but I mean, just to get an idea. So let's say that X is measuring how many people are in a bus. And there are discrete time instants because, I mean, the number of people is not changing in between two bus stops. And then every time you reach a bus stop, then there is a change in the state, right? So at the beginning, there is only one person that is like the bus driver here. So X at time 0, when the bus driver starts, it's the only one. Then we go here, we reach the first stop, and then we get the two people getting in. So X of 1 is equal to X of 0 plus 2, that are the number of people that entered now. And this is equal to 3. So the new state is going to be 3. And then we go to the next stop, and then we have one person that is dropping. So we remove one person from the previous state, x1. So x2 is equal to x1 minus 1. So we have two people, and so on and so forth. So you can play this game until whatever time you want. So you can go to infinity. And this type of model, I mean, it's a bit more intuitive than when you have a differential equation. Even creating this model, you don't need like, I don't know, a degree in physics. So it's like the next at the next bus stop, we have the number of people that were there before, plus the number of people that entered, minus the number of people that got off the bus, right? So nothing complicated. And actually, most of the models in computing systems can be created in this way, because I mean, you have always this type of reasoning. I mean, something is accumulating or is not accumulating, and then maybe there is some sort of rate at which something is decreasing. Another notable example, several people don't think really about Google Pagerank, I mean, the algorithm, the initial algorithm of Google in terms of control theory or discrete time dynamics. But it's actually quite interesting to look at this from this perspective. So let's say that you have like a set of pages, a very limited web, right? So you have only 4 pages, and they are connected in this way. Like, for example, page 1 has links to page 2 and page 4. Page 2 is connected to page 3. Page 3 is connected to page 1, and page 4 is connected to page 2 and 3. And the fundamental idea behind the Google Rank algorithm was that, well, the importance or the relevance of a page depends on how many links are going out and how many links are going in the single page, right? So the more connected you are, the better you are, because several people, especially if they are connecting to you, then this is going to be quite relevant. So you can model this as a graph. And then this graph is sort of telling you what is the probability that, for example, from page 1 I mean, if you are in page 1, you can go to page 2 with probability 1/2, or you can go to page 4 with probability 1/2. Or, for example, if you are in page 3, the only link that is going out is to page 1. So with probability 1, you go there, right? So if you put this in mathematical notation, and then if you try to model how people are clicking in this very simplified network, it looks more or less like this. So practically, you sort of get like, if you are in page 1, you can go to page. So the first row, sorry, the first column is related to page 1. So the first from page 1, you cannot go to page 1. You can go to page 2 with the probability 1/2, or page 3 with probability 0, or page 4 with probability 1/2. And then you fill out this matrix. And then you get like a kind of a special matrix. It's called a stochastic matrix. I will not bother you with this. But the important thing is that if you write this type of system, this sort of accumulates over time what is the probability of being in a state. So you sort of analyze this sort of system that you don't have any input. It's just like how the system is evolving over time. Actually, this looks also like a Markov chain, but I will, again, we don't go there. So the idea is that if you call this the matrix A of the system, A is built in a way that is kind of special. As I told you, it's called the stochastic matrix. And if you compute the eigenvalue of this matrix, there is always one eigenvalue. No matter how many links you have around, you have always one eigenvalue that is equal to 1. And the ranking algorithm is kind of saying, OK, let's try to understand what is the probability of being in a specific page when time goes to infinity. So whenever you practically reach the steady state of this type of system. So you can compute it by setting that the next value is equal to the previous value, and then practically you solve this type of equation. And actually, this type of equation is nothing else but the definition of what is the eigenvector of the matrix A. And I promise that I will not mention any more about eigenvalues and eigenvectors or eigenspaces or whatever. It's just to tell you that the problem or the algorithm of of PageRank is nothing else but the computation of the eigenvector of a matrix. Okay, you can do it very simply like this, and it doesn't require like a crazy idea. But I promise that I will talk about control. So let's go back a bit. So I was speaking about discrete time systems. I hopefully I convinced you that they are kind of interesting to look into. And typically in control, you have seen something that is, for example, a PID controller that may look more or less like this, probably. And you spend like a full semester looking into how this formula is obtained and maybe how to draw both the diagrams, Nyquist diagrams. I mean, you probably didn't really understand why you were doing that, right? And also you reach something that at the end of the day, it's an expression that, yeah, you don't really understand what it is. And especially if you reach like a transfer function like this one, you don't really know what are the implications, or what is this? What is this object? It's a function. It's something that I write on a paper, but I don't really understand what it is, right? So this is a common problem in control courses. So I think it's important to rethink a bit how people are teaching, and I put myself as well in this category, how people are teaching control courses. What is a controller for real? It's something a bit different. It looks more like this. So in practice, a controller is nothing else but a function that you write in like a bigger software system, nothing else. The point is how to design the function that is written here. So practically, you typically do like the control loop that you read the sensors. You typically compute an error that is like the difference between what you want, that is the set point, typically called, and what you're measuring. So if the temperature in the room is not what you want, there is an error. And then you feed this error, this information to another function that is this compute control load that you want to compute. And then you apply the actuation, and then you wait for the next sample. And I will forget about the continuous time part, because I think it's more interesting to look at the discrete time controller, because I think it's a bit more intuitive also in terms of algorithm. And then the same algorithm looks more or less like this, which doesn't look much better, but it's more or less how it looks in discrete time, the equivalent of the PID controller in discrete time. So you compute U of k, that is your control action, your next action that you apply, based on some parameters Kp, Ki, and Kd that are the proportional, integral, and derivative parts. And they are called like that because, I mean, Kp is multiplying the error. So you take an action that is proportional to the error, how much error you measure between the desired temperature and the actual temperature in the room. But also you have something that is like the integral of the error. That is like you are accumulating the error over time. And also you are computing something that is the derivative that is kind of, that it looks like this. And h is the time in between the two samples. So this is a very common controller. And I would say that it's 90-something% of the controllers out there in the physical world as well are designed as PID controllers. But we will look also a bit into model predictive control. But there are several other types of controllers. So we will not extensively look at all type of control systems because, I mean, this will take much more than the time that we have. Is there any questions so far? Everything crystal clear? Am I speaking too fast or too loud or too, I don't know. So I want to elaborate a bit, and I promise that, again, this will be the last time you will see a lot of equations. But I want to elaborate a bit on this equation because I want you to remember somehow what I'm doing. So what I have here is actually what I wrote before. That is the classical view of the PID controller. But then let's rewrite this by just changing the value k. So we replace every time we see k, the time k, with the previous value. So we write u of k minus 1, e of k minus 1, e of I is, we are actually shifting the time index here, and then here in the derivative part. Now what we do, it's another step, which looks super complicated, but what I actually did was I take this on top, and I removed from this on top the one on the bottom. So it's u of k minus u of k minus 1. So this is what I get here. And then Kp minus Kp, this part, and this, and this, and this. So all of this simplifies to a fairly simple expression. So let's forget about the d part for a second. But u of k, so what I'm writing here is u of k, the action that I'm taking now, is equal to the action that I took before, plus some correction that you are taking. And this correction is proportional to the difference in the error that you are experiencing and the current error here, and then some other function. So now this is the basics of most of the controllers that one can design and that can solve a lot of very important problems. Of course, if you set Kp or Ki or Kd equal to 0, not all of them, but some of them, then you get, like, for example, the proportional controller, integral controller, derivative controller, and any combination thereof. And what does this mean? This means actually that you can write this compute control law in this way. So the compute control law is taking as an input an error, double E, and then you are saying that u is nothing else but u is equal to the previous value, and then you're adding the contribution of the proportional, the integral, and the derivative in this way. And then you save for the next iteration the state or what you need, like from the previous value, like eprev is like the previous value for the error, and then you save it, and then you return the current value of u, and then you will sort of reiterate continuously this. So it's kind of fairly simple. And if you have ever tried to implement maybe a neural network or a reinforcement learning algorithm, it's not that simple. Okay, and it's not that simple, but it's also not that predictable, the type of behavior that you get in terms of execution time, in terms of energy that you're consuming, in terms of many other factors. So this function is really like just these few lines, and then the whole course of control theory that you have studied is just trying to tell you what is Kp, what is Ki, and what is Kd in a sensible way. How do you choose this value? And that's it. So if you think about, for example, a neural network is the same as, for example, tuning like the weights or tuning some hyperparameters of a reinforcement learning algorithm and these type of things. There is nothing else, but the function is extremely simple. And I will skip some other parts. I will not go into several details, especially because I don't have. Yes? Do you want a microphone or?
as a computer scientist,
yes.
What about generalizing this so that the return here is not just a double? How can I generalize this? Because in general, when you control a computer system, you not control it just with a double. It might be something more, involved.
Yes.
Do you do this?
Yeah, that's a very good question. So it's one of the fundamental, I would say, not limitations, but one of the things that one have to think how you are, what are these numbers? What is the error and what is U? It can be a generic action. It can be like I don't know, a number that is controlling some thresholds or whatever. So the choice of what is the actuation and what is the sensor in a computing system is critical for making this functional. Of course, everything that is like control related works with numbers. So you have to translate at the end of the day the action that you are taking into a number. So you cannot just put like a structure there and then say, okay, I'm multiplying a structure by 5. And then I mean, what does this mean? If you are able to define this, then yes, you can do that. But it's a design problem. And I think this is the most interesting part of applying control into software systems, because it's not really a matter of designing new algorithms. The algorithms are out there, but it's how to use the algorithms that are out there in a smart way so that you can sort of map numbers to some more complex structures. Yeah. Good. Yes?
Can you give us an example about how this relates to the Pagerank algorithm? So before you mentioned that with the Pagerank, you want to predict the future page. So how does the two relate?
Yeah, it's a good question, and probably I was not that clear on this. So there are two things. One is the plant that you are modeling, and you are writing a model of the plant, and then you are trying to analyze how this plant is behaving. And that is what I was trying to do with the Pagerank algorithm. And the other thing is the controller. That is another block. So I moved to a different block that is trying to control the behavior of an algorithm. Now, what is interesting is that knowing that, for example, the network is done according to the graph that I showed, can you insert kind of a bias in the way, for example, the probability of clicking on a specific link? Can you add kind of a bias to some links so that you are going more towards a specific pages or increase the probability of getting to a specific page? And that is kind of very important, and there are several people that are studying this. For example, there is a very nice group with Paolo Frasca in University of Grenoble that is actually studying how you can actually affect the perception of people by showing them some, for example, colors or advertisements or whatever, so that they would prefer always one link to another. So you can affect these probabilities of clicking on one link or another. So that's kind of the coupling of the two things. But what I was presenting is just like the bare plant. So you have these links, and then these are the probabilities and in a uniform way. I can repeat the question in case. So if you don't feel comfortable speaking in English, you can take it in Italian and I will translate.
So in the end, the U value is like the correction bias you apply to the link, right?
Yes.
Okay.
Exactly. Any other question? Don't be afraid. And as I said, if you don't feel comfortable with English, it's okay with me, at least in Italian. I know that I shouldn't say that. So I mentioned also another type of controller that is typically not taught in basic control classes, but I'm going to speak a bit about this in a second. And it's this model predictive control. That looks like a super complicated algorithm and quite fancy, like you're speaking about predictions and stuff like that. But everything boils down to the fact that this algorithm, this compute control law, is nothing else but an optimization problem. So I don't know how many of you have taken courses on optimization. Some of you, okay. So if I'm speaking about optimization, I mean that there is typically a function, like what you do in calculus, and you want to find the maximum or a minimum of a function. You want to find the optimal value of a generic function. Think about this function as being the cost of something, and then you want to find something that is minimal. But it's a bit more complicated because sometimes you just don't have this function, or you may have this function, but you may have also some constraints on what are the values that you can pick, okay? So I will speak a bit about this objective function, that is the function that you want to minimize or maximize, and there are some constraints. And the idea of the model predictive control is that you should have a model, and the model is exactly the same as the model I was showing before. And I mean, typically it's written like in this form as I showed before. And then, for example, it can look like x of k plus 1 is equal to minus 0.5 plus u, and y is equal to x. As simple as that. But then there is a predictive part. And what does it mean, the prediction? How do you predict the future? Well, if you have a model, you can use the model to understand how your actions are going to affect the future, okay? And the idea is that you unroll the model dynamics. What does it mean? It means that at time 0, you write this one. So x of 1 is equal to a x of 0 plus b u of 0, and y of 1 is equal to c times x of 1. But then x of 1 is equal to this formula here, so you get something that looks like this. You just sort of plug it in and then get this. Then you can do the same for x2. So x2 is equal to a x1 plus b u1, and y2 is equal to c x2. But x1 you calculated before and is equal to this formula here, so you can plug it in and then you get this. And then x2 you computed now and then you put it here. And then you sort of unroll this over and over and over. And then what you get is that no matter what is the time instant, what happens is that the value of the state and of the output of your system depends on the current state, the initial state, according to some function of a, and u of 0, u of 1, u of 2, that are all the actions that you are going to take, right? And you don't know these actions. So what you want to do is to find this plan of actions in a way that you are optimizing a certain behavior, okay? And then, for example, I mean, with a numerical example, you get like this system here, and then this is going to be like this, and then, I mean, I can sort of, you can plug the numbers, and then you get all this in this form, right? So the fundamental idea is that you can use this to predict the future based as a function of what are your actions. And you want to find the best actions you can so that you are minimizing a certain function. Now, minimizing what function? Well, the function looks like this, which looks very weird. So forget about this Qi and Ri. I will not talk about this, but they are just like weights to give importance. But practically, you have two components here. So the top one is called this objective function, and it is trying to minimize the difference between this y with a circle that is typically indicating the desired behavior of the system. Think about this as the temperature that you would like to have in the room, and y, that is the actual temperature that you're measuring over time, right? And u is another component that is added to this cost, that is how much energy, at the end of the day, it's related to how much energy you want to dedicate to control the plant, okay? The other thing is that you don't have full availability, you don't have full control of how you do this, how you are controlling your plant. Sometimes you have some limits, like for example, a heater cannot go more than 100% of its own capacity, or you cannot turn it off more than off, right? So you have some limitations on how you can actuate. And sometimes these limitations are not only like in terms of minimum and maximum, they can be even in terms of how fast or how much you can change at every time iteration. And the last thing is, well, this is subject to the fact that you are bounded by the dynamics of the system. So you have to use this model that you have of the system to understand how your actions are going to affect your system all over the place. And everything is kind of what I write here is that I want to minimize this objective function subject to some constraints that I have here. And you can add even more constraints if you have them. And you want to find what are the values of u. So what is your plan of actions so that this output is as close as possible to the desired output. And technically speaking, one can prove that this is equivalent to a quadratic programming problem. If you know what I mean, it's okay. If you don't, just forget about it. But at the end of the day, I mean, enough with the equations. What does it mean? It looks very much like playing chess, right? So the type of approach that you have here is like playing chess. What do you do with when you play chess? You try to plan in advance what are your actions, and then you try to optimize your strategy so that you are reaching your goal, that is winning the game. Now, for example, in this case, winning the game means that you are reaching a certain value with y, that is the dotted line. So you want to get there eventually. You don't know when you will get there. You want to get there as fast as possible. And then you have experienced a certain number of values that are like the moves, for example, that you took during a chess game. And you have taken some actions that are, for example, these actions with you. Now, this is the past, so you cannot change the past, unfortunately. And you look into the future. Now, of course, if some of you have done some courses with AI and search algorithms, you know that, I mean, you can try to sort of explore all the possible solutions, but I mean, it branches quite fast, and then it's getting very complicated, and you will never be able to explore all the solution in a reasonable amount of time or with a reasonable amount of memory. So you typically have a prediction horizon that is kind of similar to the how many levels of the tree you are exploring while searching for the best strategy. So the idea is that you look into the future, and then based on the model, you sort of predict a potential behavior, and then based on this potential behavior, you take the strategy that is making you achieve this type of behavior, okay? And then what happens is that you select over all the plan of actions, only the first action in your plan, okay? And this is typically called a receding horizon approach. So you compute a whole strategy, but you only use the first one, the first element in your strategy, the first action. But then you apply that action, and then you see what is the actual behavior. So you take a move in a chess game, and you see what is the actual counter move of your adversary. And then this move can be what you predicted, or it can be something different. So it is okay if it's not what you expected. It can be that you didn't expect this specific move, and then your adversary is a bit dumb, and then you are actually getting closer to your goal. Or it can be that your adversary is very, very smart, and then you are a bit more far than you expected. And then what you need to do is to say, okay, let's start from here. This is the new state. That's my new past. What is next? And then you iterate this process over and over and over again. So you solve this optimization problem, you find the whole strategy, and then you apply the first element in your strategy, okay? And you look in the future by using the model that you have. Any questions related to the model predictive control? No. Or even online, if there is anything, just let me know.
Can I ask you a question?
Yes.
When would you use model predictive versus other more traditional control strategies like PID?
So the question is, when do you use model predictive control against other controllers? And that's a very good question. So model predictive control is very nice, but differently from what I've shown you before for the PID, that you have like a very simple and self-contained function. This model predictive control requires at every time to solve an optimization problem, which is typically very heavy, and it's typically very demanding in terms of computational power. So one first thing to think of is how much computational power and how much time do you have to compute the next action. The second thing is if you have or if you want or if you need a notion of optimality of your solution. And the other thing is related to the first point, how frequently you need to compute the next action. So in terms of timing, if you need something that is extremely fast and that is kind of working fine, but it's not necessarily optimal, the PID controller, for example, or similar, are a better choice. But of course, it can get even philosophical because, I mean, we are getting more powerful hardware, and then it can be that you have like an FPGA or similar that is kind of very fast in computing the solution for an MPC. And I mean, we can go on and on with this, but let's say in general, this is the type of reasoning that one can do. Did I answer your question?
Perfectly. Thanks a lot.
Good. Do we need a break, or do we want to have a break?
We'll go straight.
Some people were like, yes, no.
No, you're not taking a break. You're taking a break after the talk.
Okay.
Trust me.
Very good. So let's dig into some examples, and I have several examples. I have several slides, but I will not go through all of them. But I want to motivate what I'm doing, or what I presented, with some more concrete use cases, let's say, of control in the computing systems domain. And for example, I start with task scheduling. And there are several publications related to that. I mentioned this one, but we have been working quite a lot with task scheduling, because task scheduling is at the basis of, for example, real-time systems. And does anybody know what is a real-time system? Real-time system is a system that has typically a certain deadline that you want to meet, and then computing by the deadline is important. You can finish any time before the deadline, but if you compute after the deadline, it's actually going to be dangerous or unsafe in some situations. So the typical example is like the airbag. So if the airbag is not timed in a proper way, then you are going to hit the steering wheel, and then it's going to be bad. So you have to time your computation very, very carefully, and then this falls under the real-time systems. And don't mix real-time systems with fast systems. Real-time systems must be predictable, but not necessarily fast. Good. So let's start from what is a scheduling problem. Some of you may know already what is a scheduler or scheduling problem, but from this perspective, ideally, what happens is that you have a certain task that you want to execute, and this task is taking a certain amount of time. And ideally, you do this task periodically, right? So for example, you are controlling the behavior. It can be a control task. You are controlling the behavior of a car. It can be that you are controlling the robot motion, or it can be whatever you want practically. So you have a continuously repeating task. But then practically, you don't have the execution time that is always the same. So it can be that you are taking a bit more time to compute or a bit less time. So typically in real-time systems, what people do is to account for the worst case execution time. That is, as the name goes, it's the worst case of your computation. And getting this worst case execution time is extremely complicated. Because, I mean, either you do some static analysis of the code, or you perform a lot of experiments, and then you sort of take the maximum time that you experience, and then you add maybe a factor of 2 just to be safe. And then it can be extremely pessimistic. Now, the point is that this execution time, even if you go for this worst case execution time, it may happen that you are executing a bit less, like in this case, or a bit more, like in this case. And if you are running multiple of these tasks on the same platform, you may experience some undesired behavior. So the idea, due to these discrepancies, the idea is that these discrepancies are kind of a disturbance, an external disturbance. It's kind of the environment that we had in the beginning representation. And you typically want to assign a certain time budget to these tasks. So you task execute for 1 millisecond every time, or every time you change how much time they are executing. You measure the actual time that they are taking on the CPU, and then you can define a scheduler that is kind of assigning continuously the same time slot like the same quantum, like a round robin policy. You just assign 1 millisecond to one, 1 millisecond to the other, and 1 millisecond to the other again. Or you can actually change how much time you are allocating so that overall they are getting the same amount of CPU. Because if you are executing a bit more, then you are stealing computation time from other people, right? So how do you model this? This is not complicated to model. This is like the execution time that you measure, let's call it x of k, is nothing else but what you have assigned to the task, plus a discrepancy that I call a disturbance, d. And typically this d is not included in the models that you have. You may want to characterize this disturbance, but that's something that just happens to your system. So your actual model looks like this. So yeah, x of k is equal to u of k minus 1, and that's it. So you don't need like super complicated differential equations to model this type of problems. And what happens is that you can, for example, use an integral controller to do that. So I'm actually writing here the exact same expression that I had before with kp and kd equal to 0. So I have only this k that is the integral term that is saying that the current amount of time that I assign to a specific task is equal to the previous amount of time that I assigned before plus k, that is a parameter that you have to choose, that is multiplying what? The target budget of time that you would like to assign ideally to every single task minus what they actually took during the last execution, okay? And what is interesting is that this equation, I mean, now that I've been talking now for an hour, this, you know that it's an integral controller, but if you read several papers out there of computer scientists that do not have necessarily a control background, they write some very complicated algorithms, but at the end of the day, they end up doing something like this. And then they say, okay, this algorithm is called like super fancy scheduler with proportional budget allocation and stuff like that, okay? So it can get super fancy, but at the end of the day, it's an integral controller. And I challenge you to look into several of these papers and then look at the algorithms a bit more carefully, because several times this happens. I mean, it happens so often to me that I'm actually surprised that we are reinventing the wheel over and over again. So, yes?
You're saying that even if I take some of the most complicated algorithms of scheduling for kernels and stuff like this, I could reduce them up to an integral controller of which I only control a key, which is a number.
No, I'm not saying that any algorithm can be represented in this way. I'm saying that several times, some of the algorithms that are published, if you sort of write the equations and then you put them together, they end up looking something like this. Even, for example, if you think about the learning process when you are adjusting some algorithms, some reinforcement learning algorithms, you have something that looks like the weights are equal to the previous weights plus a learning rate times a certain error. So it's just an integral controller, just to give a notable example. And actually, several times you say, okay, the rate should be within a certain range, otherwise this will not converge, and that's related to the stability of the control system. So everything is connected, so I used to say. Good. So with these two things, so the simple model that I showed you, and this simple strategy for controlling the time for task allocation, we wrote the paper that I mentioned at the beginning that provides hard real-time guarantees. What does it mean, hard real-time guarantees? It means that no matter what, if you bound the error or the discrepancy, so you have some estimate of how much you can deviate from the original plan, you can find the worst case allocation or the worst case scenario and then guarantee that no matter what is the behavior of the system, you will always meet the deadline, okay? And this is extremely simple to implement. So it's not complicated to write this stupid function. It's just like one line of code. you don't have like a neural network or super difficult nonlinear functions to implement. So that's quite cool. Second example that I want to show is, I will dig a bit more into that. It's the clock synchronization. And the clock synchronization is a fundamental problem in computer science. I mean, it has been investigated and there are several solutions out there. I mean, we were focusing on clock synchronization in wireless sensor networks, but similar ideas can be applied, for example, in wired networks and, for example, in Ethernet-based or time-triggered networks. So I will speak about this only in the wireless sensor network domain, but if you are interested in working a bit more on this in other domains, just let me know. So what is clock synchronization? Maybe not all of you are familiar with this. It's a classical problem in computer science. We go back in the 70s and 80s when, for example, Lamport started talking about this. And recently, in the late 2000s, several people, even in control, they started being interested in this type of problem. And the problem is like you have like several nodes in a distributed network and you want their clock to be synchronized. It's like a set of friends that want to meet somewhere at a specific time, and each of you have a clock, and then you want to make sure that you're meeting at the same time. You need synchronized clocks, because if your time is different, like by 15 minutes or 1 hour, then it's a problem. And of course, in computer systems, several algorithms in distributed systems are assuming that all the clocks are synchronized. So it's a fundamental problem, because if it's not working properly, this will break most of the distributed system algorithms. For example, it is important for event ordering, event interval measurements, but also for low power radio operations. So there are several other reasons for that. But the problem at the end of the day is that you have a set of networks, a set of nodes, wireless sensor nodes, and then you have a clock in every node. And we are focusing on a master-slave architecture. So there is a master node that is like the one that is telling the truth, even though it might be wrong the time. And all the others are the slaves. And you want the time of all the slaves to be exactly the same as the time as the master. So all of them should be the same time. The problem is that every single node, I mean, you can synchronize them at a specific time, but then every single node will experience a deviation. So my clock will always deviate a bit from your clock and from someone else's clock, okay? And the reason for that is that sometimes there is an offset, I mean, maybe a very minor offset, and then the error in milliseconds can be like just a constant error, and that's not really a big problem. It can be compensated easily. But it can be also that there is a minor skew in the how time evolves. What does it mean? It means that, for example, I have like a quartz in my clock, and it is oscillating a bit less frequently than the quartz in another person's clock. And then over time, this difference will sort of deviate quite a lot. You may have some drift due to several different reasons, and then you have also some jitter that makes the error even more unpredictable. So all in all, what happens is that if you just synchronize two clocks and then let them run, you will always have some error due to these reasons mostly. And there are several algorithms for sort of controlling this behavior. These are like some of the most commonly used. Even in your laptops, there is a master node somewhere, and then you are connecting, and then it is synchronizing the time on your laptop. But what they are all related, or they are all based on the fact that you are fixing your local clock somehow. So the idea is that if the master is saying, well, it's 2:32, that close, we are a bit in advance. It's 2:32, and your clock is saying, well, 2:43. What happens is that the master is sending you the information about the clock, and then you are overwriting whatever you have here, and then saying this is 232, plus maybe a correction, because maybe you know something about the network, and then maybe you are compensating for a delay that you are experiencing. Typically, this is not a major problem, because I mean, signals are traveling quite fast, and then the resolution of the clock is not that fine-grained. So, but you can have a correction, for example. The problem is that if you do that, you are overwriting your clock. So you thought that it was 2:43, but now your time went back. So you went back in time. And then if you were ordering some events, maybe you are counting how many people are in the room for every second, then you might get some count that is a bit off, just because you are going back in time and you are continuously fixing this. So you are not really sure what is happening, and you would like your clock to be monotonically increasing, meaning that you are never going back in time. You will never sort of grow and then go down and then grow and then go down and grow and then go down, or maybe up. Then you have a gap. So you would like to smoothly change your rate of change in the time. So the idea is fairly simple. We can use virtual clocks, for example. This is not a new idea. It's something that has been done even in the past. But the idea is that every slave has a local clock and a virtual clock. So the local clock is whatever it is. I mean, it's the time that you measure in your clock. The virtual clock is a function of the time that you see here, and then you sort of correct the time in a way that is going to be a smooth correction and monotone correction. So that's exactly what I said. So the virtual time is nothing else but just a function of the local time. And the function is continuously updated, but not like in a continuous way, like at discrete events, every minute, every 60 minutes, every X amount of time. And the update must guarantee the monotonicity, and we don't want to base the update on timestamps. Does anybody understand why we don't want to use timestamps? Do you have any idea? You can try to guess. So one thing is related to security. For example, if somebody is like spoofing some of the master messages and then changing the message that I'm receiving, I can deviate the time of the slaves just by changing a bit the message of the master. That is one reason. The other thing is also that sending a signal that is empty, it's energy efficient. You don't have to send much more than just like a bit, and that's it. And the other reason is that yeah, we can look at the other reason later. You can think a bit more about this in a second. But we want to send empty messages practically. So the only thing that you need to know for this application is that you have a synchronization period. So you as a slave, you agreed with your master that every minute, every hour, you are receiving a bit. And you are not trying to interpret the bit, okay? You're just receiving that bit. And then in order to receive a bit, you have to open the radio channel, and you have a certain window of time in which you are receiving messages from outside. And then within the window, you are receiving the synchronization packet. And how does it work? It works like this. So you have like the master that is sending according to the usual protocols. You are expecting to receive, according to your clock, you are expecting to receive the call from the master at this time, but then you want to be a bit more resilient, and then you open a bit earlier, and then you close the window in which you are listening a bit later. And then at some point you are receiving a message. And then at that point you measure what is the time at which you receive the message, and you measure the time that you expected to receive a message. And then you can compute an error in between these two things, right? So what happens is that you will open again, or you are expecting, you compute what is the next time that you are expecting a new message, that is t seconds after. Then you are repeating again, you are opening and closing your radio channel, and then you are computing a new error. The idea is that this looks more or less like this. So you have the local clock that is estimating the next time at which you are receiving a packet as the previous local clock estimated time plus t, that is what you agreed with your master, plus u, that is a correction that you are making to the estimated time. And yeah, this is the expected arrival time in local clock. This is the synchronization period, and this is the the correction. And then if you solve this this equation, this looks more or less like this. I mean, I will not try to solve the difference equation right now, but you can understand that it's like k times t plus the sum of all the corrections that happened over time. What happens to the actual clock, what I indicate here with the TA, it's that the actual clock is going to be kt plus something that I have no control of, that is like the errors that I was showing at the beginning. So you have a drift, you have like some offset, you have the skew, the jitter, and whatnot. And then this is accumulated over time. So this is actually something that is computed over time. So that's why there is an integral. It's something that you have no control of. So we are going to sort of boil this down into something that is just an external disturbance. So what happens is that if you make a difference between this and this, you are just computing the error that is feeding your control algorithm in the end. You are like ending up with the sum of all your corrections over time minus this thing that you have no control of. So you are trying to cancel out these disturbances with the sequence of corrections that you have here. And then if you do the math and reach at the end of the day that what this is the expression is that the next error is going to be equal to the previous error plus the correction plus a disturbance that is happening to your system. So I'm not going to explain this, but the idea is that you have a very simple equation at the end of the day that is modeling how the error, the synchronization error, is evolving over time. And you would like to control this. And as I did before, the disturbance is something external. So you don't measure it. You don't try to measure it. You just experience it. And then you react to that based on what you're actually measuring. And I mean, I could probably avoid having all these equations, but it looks cool to have equations in slides. So I put them there, but you can even figure out the same equation by reasoning. So I mean, what I'm trying to say here is that, I mean, this looks very formal and complicated, but the synchronization error is what? Is what I accumulated in the past, the previous error, plus the new contribution to the error that I have now, and then I can add a correction that is plus u that I have there. So I don't need to put together integrals and stuff like that. Now, I mean, this is the transfer function of that you get out of this, but yeah.
What if I don't receive a synchronization message while my window is open?
What if you receive a synchronization message?
If I don't receive any synchronization message while I kept my window open?
Yeah.
So I open the window, wait, close the window, nothing received.
Yeah, that's a good question. So if you don't receive the synchronization message because it falls beyond your window, then you are not trying to correct anything. You are just trying to keep things as they are. But then if this happens too many times in a row, then you reset the system and then you call for a full resynchronization of the wireless sensor network. So that's how it works in practice. And actually, we have implemented also an adaptation mechanism of the window so that if you don't receive it, then you are enlarging your window in the next iteration so that you have a higher probability of getting the message. And then if you don't get it again, you enlarge the window again, and then you have like let's say a number of iterations in which you can do this, and then you stop because you cannot just enlarge the window. There is something wrong, and then you have to stop.
what if the clock is perfect, but the network is really bad, meaning that you are correcting the clock, but due to external error, not your error?
But in that case, what would happen? You still experience a longer delay in the communication towards the master, and then the master still has a functionality of collecting some of the data that the slaves are collecting throughout the wireless sensor network. So still you are trying to compensate possibly for some network imperfections, but that's something that it's my gut feeling to your question, but it can be that there is something more complicated there. So I'm not 100% sure if that is the case. Any other question? So yeah, I will go very fast on the control synthesis, because here we didn't use a PID controller, or we didn't use an MPC. We used a kind of a custom-made controller, and everything boils down to a function that looks very similar to the PID controller. So you can implement it as a few lines of code, but the way it is designed is a bit different. And then somehow the way it is designed is based on the disturbance characterization. So you know that there is a disturbance that is happening, and you can model the disturbance somehow. So the disturbance can come from crystal imperfections. That means that this is going to affect the skew term, the aging of the device. So I mean, while aging is happening, you can have a deviation in general of the clocks, but this typically is very slow with respect to the synchronization period T. And their effect vanishes if you select something in the design. There is a short-term jitter that is typically very small contribution, so it's typically not affecting so much the design. And then in principle, you can take into account this in the design of the controller. There's a propagation delay that is typically negligible, but in some applications, it can be a bit more sensitive. And we actually dealt with the propagation delay. And the other part is the thermal stress. And the thermal stress is a bit more interesting, because the thermal stress is something that several algorithms for wireless sensor networks are dealing with in an explicit way. And they try to put in the node some additional sensors to measure what is the temperature within the sensor. Because I mean, temperature is going to affect quite significantly how fast your time goes according to your clock. And I mean, you can think about this as boxes. I mean, the wireless nodes are typically within boxes that if they are deployed in an outdoor application, then the temperature can make this box very, very warm or very cold, depending on the weather. So in principle, I mean, I will not look into these equations. I don't worry about that. But what I wanted to say is that you can design the controller in a way that you are accounting for all these disturbances. And you can even tune these parameters by, I mean, we developed like a tiny tool to choose these parameters in a proper way based on your requirements. But typically what happens is that whenever you have a step in the thermal stress, meaning that you have your node deployed outdoor, and then there is typically a sun to shade transition. So there is a cloud that is passing in front of the sun, and then all of a sudden there is no radiation going to the box somehow. So you are not heating it, so it goes down the temperature, and then the cloud vanishes, and then there is another gradient of temperature on the box, and then this is affecting quite significantly the temperature and the time synchronization. So all in all, we did some experimental setup. We were actually sort of emulating even the sun to shade transition and vice versa. And what we obtained in a multi-hop network was something that was quite nice and impressive. So we managed to get the synchronization error down to below 1 microsecond. And typically, the error is on average in the scale of a few tenths of nanoseconds. The other thing is that, so what I'm showing here is the shade sun transition, that the black line is more or less how the temperature is, sorry, the synchronization error is happening, and then you see that it's kind of smoother in the way it reaches zero, while these other two algorithms, they are sort of making this sort of very abrupt correction. So they ramp up, and then you make a correction because you are overwriting your clock, and then you're ramping up, and then you correct, you ramp up, and then you correct, and so on. So they follow similar patterns, but the black line is actually guaranteeing that it's a continuous correction. So your error is if this is you're seeing time like this. So if this is the time, you are kind of oscillating around the time, but you're not going back in time. So it's never going this way. And we did also something related to delay compensation, but I will not speak too much about this. But delay compensation, I mean, if it's an outdoor application, it's not very important because, I mean, typically you deploy the nodes not so far away, and the propagation delay is quite small. But if you are underwater, for example, the propagation delay is increased, and then in underwater applications, the delay compensation is going to be important. And for delay compensation, we have to use some message in the synchronization error. Yeah, some other things, but I will not speak about this. The other thing that I want to talk about, and I have still a lot of time, the other thing that I want to talk about is another application area in which we worked. I mean, I think this was one of my first contributions. I started working on this when I was a master's student in Politecnico di Milano, and we had this collaboration with MIT, and they were developing a framework that was called Heartbeat for sort of measuring the performance of applications. So they were adding some specific system calls to applications so that they could measure how much or how healthy an application was while running. And then based on this heartbeat, they were trying to control how much resources they were allocating to the application. So the heartbeat framework was developed by MIT, by the group of Anant Agrawal. And actually, if you want to know more about the heartbeat framework, there is a link there. And at the end of the day, it's just an API that is sort of either at the application level or at the operating system level. And then you typically have some application parameters or system parameters that you can sort of tweak so that the heartbeat goes a bit faster or a bit slower. So the simplest thing that you can think about is if you have a video encoder, for example, and then you want to encode a certain number of frames per second, that is somehow how many heartbeats you want your application to emit. And then if the heartbeats are a bit too high, then you want to slow down a bit the application, or if the heartbeat is too slow, then you want to allocate a bit more resources to the application. And this can be generalized in many different ways. But this is quite an interesting and nice control problem, because at the end of the day, you have your application, for example, that is running, you are measuring how many heartbeats, and then you are giving this information to the resource manager that through some system calls, you can control the resources in your application. And you can set the target heart rate, and this is a quite common control problem. So we said, okay, let's do this. So what do we choose? I mean, let's go back somehow to the question of Elias. Should we choose a regular PID controller? Should we choose an MPC? Should we choose what? Well, we chose an adaptive MPC, and I will speak a bit about adaptive MPC because there is also something that is a terminology clash between the control literature and the software engineering literature, because you have heard about self-adaptation. You have heard about self-adaptation, and then you have heard about adaptive software and so on. But then what people in control mean when they speak about adaptive control, it's something that is slightly different, that is more related to the learning part. So it's about learning something at runtime. So adaptively changing the control strategy. So the idea is to add to the classical MPC that I showed before, another layer, another block that is an online identification. That's what the control people used to call it. It's an online identification algorithm that is nothing else but a learning algorithm. You are learning the model of your system. You want to learn the matrices A, B, C in your MPC model so that when you use it for predicting the future, your model is always more updated, more accurate. And the reason why we wanted to look into this is that applications are not as nice as, for example, task scheduling or clock synchronization. Applications are actually a bit more nasty because they may change abruptly the type of behavior when you are allocating more CPU or more memory, because they can be for a certain amount of time like memory bounded, so they are eager to get more memory, and if you don't, they will not speed up, they will not increase their heartbeat. But sometimes all of a sudden they can change and then they can become CPU bounded, meaning that if you give more cores, they will get better in terms of performance. So we want to learn when this is happening and then somehow switch the strategy or continuously change the strategy based on the actual performance that we are experiencing. And somehow the idea is that this model that we learn online at runtime, we can use for making better predictions. Okay. I will not dig too much into the details because, I mean, the MPC I have presented, if you know anything about machine learning and related stuff, you understand also what can be in that block, more or less. But the idea is that combining these two things in a smart way leads to very nice results because, for example, this is an example of what the adaptive controller is doing. And actually, we compared it also with the PID controller because why not? I mean, you can use a PID controller there, but I'm not showing this here. You get better performance with this, of course, because it's a bit more complicated. You have more knowledge about your system. But then we compare it also, for example, with neural networks or reinforcement learning algorithm, that is this one. And believe me, they were tuned in the best way possible. We were actually not trying to advocate for this. We were actually trying to, I mean, there are several authors and each one of us were pushing for their own algorithm to sort of behave in the best way possible. And actually, the adaptive MPC is the one that is exhibiting consistently better performance than the others. So the idea is that you want to sort of be in the blue region that I indicate here as much as possible, and then you have also a target value of reaching a specific heart rate, a constant heart rate. Yes?
Just for the sake of discussion, how do you manage in your paper to write something different than, believe me, they have been tuned the best way possible? I mean, how do you convince, how do you assess that it is so?
Yeah, so the tuning or the design of these algorithms was optimized. I mean, they were designing specific hyperparameters tuning algorithms for optimizing their performance. So this is described in the paper. So of course, I cannot go deep into these details because it's beyond the scope of this talk. But yeah, I mean, that's why I said, believe me, but all the details are in the paper. And the way it is like they were trying to optimize the same cost function, and then they were trying to optimize the behavior of the three different algorithms based on the same parameters somehow. Not parameters, sorry, objectives. Does this respond to your question, or?
It is just curious to me the fact that okay, you can prove that with a given. For instance, in the case of reinforcement learning, just to make an example, with a given Q table, you can achieve certain performance, right? But it's very difficult to state that this is the best Q table you can have for the problem at hand. This is very difficult to convince someone that you cannot do better than that.
Yeah, I definitely agree with this. The point is that what you do is it took quite a lot of time. What you do is like trying to set up an optimization problem that is getting as a function evaluation the actual experiment, and then you sort of make a gradient descent like approach to sort of optimize the performance over the specific experiment. So that is the way you do it in practice. But it takes a lot of computational time because you have to run the experiment and you have to set up the optimization problem on top of the experiment. Any other question? Even online? I don't know if I haven't looked much at the chat, but yeah. Good. So I want to give maybe one last example. I have another one, but I will not look into that. I think this one is kind of nice because it goes in the direction of abstracting. I mean, I told you at the beginning, if you are close to the hardware level, like, for example, at the clock synchronization part, or maybe even the task scheduling, things are a bit more understandable. But the more you get away from the hardware, then things are getting a bit more nasty. And then this application control with Heartbeat was going somehow in that direction. And brownout is actually something that I was not involved in the initial development of brownout, but I've been working a lot with brownout and the people that developed brownout. So it's about looking a bit more towards the cloud and then how things are happening in the cloud. And there are several different problems that I've been working on in the past years, including load balancing, auto-scaling, fault tolerance, and you name it. So several problems are out there, and they can be tackled with control-based approaches. One of the big challenges is what I was saying at the beginning. So we have to remember that the workloads come from the behavior of people, and somehow the workloads can be extremely predictable. Like, for example, the top one. The top one is the behavior of the incoming requests per minute on a Wikipedia page, or actually on an aggregate load on Wikipedia for a specific country. And then you could see that over different days, you have like some sort of sinusoidal, very regular behavior, because of course it's like kind of day and night workload. So people typically look at Wikipedia more during the day, but then of course there are some people that look at Wikipedia pages even during the night. And similar things can happen, for example, for Netflix or similar services, because I mean, usually you are not watching Netflix during working hours, usually. The other thing is kind of the opposite behavior that is kind of very unpredictable. This is actually a workload that Google released several years ago now of a Google cluster, and somehow it's very difficult to predict what is coming next. So if you're able to predict what is happening in the next few minutes, then you are also able to predict earthquakes or similar stuff. So it's very, very difficult. The other thing is flash crowds. Flash crowds are kind of an in-between behavior. So what happened when Michael Jackson died was that for some reason everybody was like, oh, let's go on the Wikipedia page of Michael Jackson. And you have this big surge of people in 2009, in June 2009, and this is when he died, and everybody was like looking into that. And then what happened was that Wikipedia went down because of that, too many requests. And similar things happen also to Google and several other services. Then there is a second peak that is out here that is going a bit high, not as high as the first one, but can you understand what it is? The funeral. So whenever, I mean, when he died, everybody was looking into that, and then, yeah, everybody knew, and then things were getting better, and then everybody was speaking about his funeral, and then everything started going back to, let's look at who he is, or what he did, and whatever. And then it went back to normal. So this type of things are very unpredictable because, I mean, you don't know when somebody's going to die or when an event is going to happen. And then all of a sudden you get tons of new requests. So can you get some inspiration from how other domains have handled similar situations? Well, do you know where this place is? Who says Paris? That's not Paris.
Vegas.
That's Tokyo.
Tokyo.
It's the Tokyo Tower. So Japanese people are extremely good with electrical networks. And what they, I mean, this is a Tokyo Tower. It serves like an antenna, as an antenna, or it used to be like an antenna, big antenna for the television in Tokyo. And regularly they lit up the tower because it's just beautiful to have it lit up. That's it. There is no functionality in that. But in the case of an electrical surge, like everybody's like turning on the air conditioning or there is need for more electricity, then they dim out the tower and then they sort of manage to compensate a bit. Not completely, because of course if it's a big surge, then it's going to collapse and it's going to be a blackout. But then they do have this concept of brownout in electrical networks. Now, brownout, I mean, the name could have been a bit better. I mean, I don't like the name, honestly, but it's an idea of dimming out some of the things that you don't need in the case that you are in need of additional capacity because you are sort of serving more requests than usual. And then this can be handy in some application areas, like, for example, in Amazon services. I mean, now this is a bit outdated, this slide, but what happens is that whenever you're browsing for content on an Amazon website, you get typically the page of the item that you're looking for, and you get also some recommendations of things that you might be interested in buying. And this additional content, you didn't ask for it. You didn't want to know what other people have bought if you were buying a Kindle. Of course, you might be interested in some of the items. And actually, it has been shown that if Amazon is showing this additional content, then you are going to, Amazon is going to make 1.5 more revenue. So it's translated into more money that is going to Amazon. So showing this optional content is very beneficial. So if you have the capacity, the computational capacity to do that, you should show this. But what if everybody's going on Amazon because there is a new device that everybody's wanting to buy, and then it's better to show an Amazon page and then sell the device rather than not showing anything at all to anyone because the system collapsed, right? The idea is, why don't we design a controller to control, based on the current income of requests, how many or what is the percentage of requests that I'm serving with the optional content and how many I'm serving without the optional content. And what happened was that we actually did this, and we showed that, I mean, we didn't change the workload, but we showed that in the case of a shortage of capacity, whenever there is, for example, like some servers that are failing, or maybe you have a data center that is not accessible, then you can still cope with a regular workload and then still serve requests with at least the mandatory content. And then whenever things are getting back to normal, then you can get back to serving also the optional content. Yes?
Besides deciding how many get the full content and how many get the shrink down version of the page, can you also decide who?
You could. It's more related to the actuation part. So this is an interesting point that you're raising. So this is a common view from a computer scientist perspective to focus on the specific detail of who should get what, for example. But I'm not interested in who is getting what. At the high level, at the decision-making level, I'm just saying no matter who is connecting, this is the amount of people that I can serve with the optional content and without the optional content. Then what happens is that this decision, that is a number, as we were saying before, it's like a percentage, then this can be translated into an action that is, for example, if you are a gold member or a prime member of Amazon, for example, you are getting also the optional content, and then if you are not a prime member, you are not getting the optional content, something like that. But that's an additional algorithm that is taking as an input the percentage of requests that you can serve with optional content, and is translating it to something that is a bit lower level in terms of policy, which is equally important. I'm not saying that this is not important, but it's at a different level of abstraction that is not interesting for the control problem. Because if you start digging into that, then it's going to be complicated to say, okay, these people are getting better performance than these other people. It can be possible, but it's complicating things.
I guess that if you also do that, you add complexity, so you might require more resources.
Yes.
Which in turn influences the control loop then.
Yeah, it's a design choice at the end of the day. So I'm not saying that it's wrong. It's just it's up to the designer. So there is always a lot of space for design choices. I will not speak about stream join applications, but I will briefly mention that this is a bit more recent work that we have been doing with some people at Chalmers, and they are interested in data streaming applications. Data streaming is different from video streaming, so it's don't think about YouTube or similar stuff, but it's more like databases and queries that you are running on streams of data in a continuous way. And then we were sort of thinking of how to create a model, I mean, similarly to what I did, for example, for the clock synchronization case, so that we can model stream join applications. And this model turned out to be not as simple. I will just show you a few of the equations. I mean, these are like few of the equations that are in the paper, and this got very, very ugly. So I mean, I don't suggest that you, I mean, if you really want to sleep overnight, you can start reading this paper. It's perfect. I mean, it's very nice paper. It's science, but of course you have to be really into this type of things if you want to hurt yourself. But the good thing is that if you start modeling with some equations and then you sort of try to understand what are the fundamental limitations, is that you can sort of get some models that are pretty close to the actual behavior of the system. So you can create simulation models. And then I challenge you to sort of understand where is the blue line, that is the implementation, and where is the green line, that is somehow the model that we designed. So they are matching almost perfectly almost all the time, apart from some cases related to the latency in which we are following more or less the same pattern, but then there is typically an offset that is probably related to something that we didn't include in the latency terms. But I will not spend a lot of time. If you're interested in talking about this, I'm glad to sort of spend some time on this. Yeah.
So sorry, so the idea here is to simulate like a cost model for streaming queries. So
yes.
Can you tell more about that, please?
Yeah. I mean, the idea, similarly to the last comment, is not really looking into what the query is doing exactly, like the specific, I mean, this tuple is going to be selected, this tuple is not going to be selected, but there is a certain level of abstraction related to them, for example, selectivity of the query. And then you have a parameter that is this sigma that we were showing in some of the equations here. Like, for example, here, sigma. And then most of these equations are related to how many tuples are coming into the stream. And then based on this, there is some sort of queuing theory related math. And then there are some other parameters that are alpha and beta, for example, here, that are more related to the platform. And these alpha and beta are the only parameters related to the platform that you have to measure on some specific hardware that are somehow related to how much time you take to process a single tuple or a single comparison in a join, and how much time that is beta is required to output a tuple, and then you are outputting a tuple only for the selected tuple. That's why there is sigma beta there.
So you have the hardware, you have the selectivity. Where are the cardinalities? I mean, of the two sources. So you have two streaming sources, I imagine.
Yes.
And where are the cardinalities in there?
So there are two things. There are two types of. We are getting technical. Maybe we can take this offline.
Yeah. So probably
because
later,
I think this is interesting, and probably you're interested in this specific application. But the idea is that we are modeling different types of stream joins, tuple-based and time-based windows. So depending on how this is or what type of window you are considering, then we are treating things in a different way, because of course, if you have like a time window, no matter how many tuples you get in that window, you have to process them. If you have a tuple-based window, you have this amount of tuples and that's it. And then the cardinality is fixed, apart from the beginning when you're filling the window. But sorry for this detour. We take this offline, and then I'm very glad that somebody picked it up. But the idea is that with this model, we can do something that is quite interesting also in terms of modeling what is happening. So you see that there are some spikes here in the latency. And what is happening here is that we are modeling also the overload case. The overloaded case is actually quite difficult to model. And by just writing down all the equations in a nice way, we get some nice results. So maybe the last thing that I also want to mention is that one of the advantages that one can have with this sort of modeling that is kind of in a closed form is that you can start analyzing also the behavior of your system from a different perspective and try to get some fundamental results that you wouldn't get if you were not modeling with some mathematical models. And for example, this is something that we found out by just using the model. And do I have an animation here? No. What we found out is that what happens, let's focus on the blue line here. The latency, if you are increasing the workload, the blue line is associated with one single thread. So if you are associating one single thread to process the tuples, you get the latency that when the workload is increasing, the latency decreases, which is a bit counterintuitive. But the idea is that the join, or in data streaming, you typically try to preserve the deterministic behavior of the operator, which means that you are actually waiting a bit more time to output a tuple just to make sure that there are no tuples that you have lost in the middle. And then so this can be a bit counterintuitive, but what happens is that if you are increasing the number of threads, so the latency is increasing for this specific region, and if you have an even higher amount of threads, the latency is going to increase. So it's a counterintuitive situation in which adding more resources for a given amount of workload, which is fairly low, let's say, in which one thread would be enough, adding more resources is not going to help, which is opposite to the experience that you get in most of other computing system applications. And the reason for that is related to the determinism. Of course, what happens is that if the workload is increasing a bit beyond what is the capacity of a single thread, then the latency is going to spike because you are not able to sort of process the tuples that are queuing up, and then the latency is going to spike. And then it's better to switch to the higher level, and then you get another allocation. So the idea is to sort of design a controller, and we actually have a paper about that is currently under review. So if you are a reviewer, connected. We resubmitted the paper Friday last week. So we were actually trying to use this model to do some elastic or to obtain some elasticity of the number of threads and some other resources for the string join application, and we were trying to exploit this model in the best way we can. So I will not speak about this. I have a lot of slides related to this, but I will not speak about this. Everything that I told you today is something that you may say, well, cool, but I mean, I don't know how to use control anyway. So how should I work with control with software systems? Which is a legit question. And it's not only you, I mean, it's everybody that is not expert in control. And maybe you don't know which controller is best to use for what situation, or maybe you are not really sure how to tune a specific controller for the specific application you have. And we have done also some work in trying to understand how to automate as much as possible the design of control structures and the design of the control algorithms for multiple actuators. So you might have multiple resources or multiple knobs that you can play with, and maybe you have multiple goals that you want to achieve. So we wrote this paper, and this is the only thing that I will mention about this, in which we are discussing about how this process can be automated and it can be as sort of used as a guideline for non-experts of control. And I think it's a nice piece of work, because I mean, it is compared with several other papers that are out there that are trying to do the same, because at the end of the day, you want to provide a tool that even a non-expert person can use. So I will quickly, can I get, so I will not go into this because I have no time, or better, I do have some time, but I prefer to leave time to question and answer. So all in all, control has proven useful in several computing applications. So it's there are several other things that we have been doing over the years, and there are even more that are upcoming and continuously coming. And I think it's quite an exciting field to work in, and because it's kind of cross-disciplinary. So far we have been working, for example, with real-time and embedded systems on several different levels, operating systems, performance engineering, cloud and fog computing, and software engineering. But in principle, there is a flower of possibilities that one can have in this domain. And in general, I think it's I mean, if you are interested in working in this type of on this type of problems, I would be more than happy to talk with you. So just reach me out, and even either today or even via email. There are several current challenges that are out there. One is further automate. I told you that we have worked a bit on automating the design of the decision-making algorithm. But it's not only that, but it's also about how to include and model humans in the loop. I mean, we were thinking of humans just as workload that is coming. It's an external disturbances that we have to counteract, but they can be also used as actuators, for example, if there is an action that needs to be taken, or maybe as sensors that can be included or embedded in the decision-making algorithm. So they can even provide additional knowledge in the design of this type of algorithm. So including humans in the loop, it's probably quite interesting. And the other thing is also, I mean, I'm kind of like hardcore control person, but at the same time, I think that there are several things that one can do by combining control with more classical AI or machine learning or formal methods approaches. So in principle, I strongly believe that in between different fields, there can be some nice collaboration and some nice results that one can get. But then, of course, if you ask me what is my dream, would be to find sort of a general formulation of physics. So, I mean, we don't have in computing systems like Newton's law, as I said before, or conservation laws or whatever. But it would be nice to have this type of things. I mean, if I ever will win a Nobel Prize or whatever, I mean, it would be probably if I manage to do something like this, which is extremely challenging. It's probably maybe impossible. I don't know, but that's why we are here to do research, to take impossible challenges. And with this, maybe we are going towards more a more shared discipline, like combining a bit more mathematical-oriented approaches like control and maybe development of software. Maybe that's something. But all this, of course, was done with tons of other people. It was not only my work. I mean, I don't take credit of of all this work. I mean, I've been collaborating with several people, and I have learned a lot also from these people. So it's definitely important to acknowledge this, and yeah, I strongly advocate for talking with people and learning from other people, because that's the way we progress. So with this, I thank you very much, and I'm here for questions.
We're going to have a little bit less time than for the last talk, and also you will have the opportunity to talk with Alessandro in the coffee break. So I'm going to prioritize a little bit the questions from the remote attendance, if there is any. If you do, just raise your hand inside Teams. Otherwise, I'm taking questions from the room. Questions?
Everything was crystal clear.
Yeah. Also, we asked a lot of things while you were presenting, so we interrupted you several times.
It's okay.
Okay, I've got a question.
Yeah.
Which is a little bit strange, and the thing is, all the systems that you presented control based on time alone, and my understanding is that then their concept of time is a stable line that goes forward in a constant manner. I was wondering, do controllers that take a, if you will, a relativistic stance on time exist? So where basically that consider not just time, but time, space-time as a single entity?
No. The short answer.
Do you want to try to do that?
Well, that could be interesting in the perspective of, let's say, formulating a physics of computing systems. But I think one remark that I want to make is that it's not true that the control is assuming that time is progressing in a constant way. If you take the example of the bus, so the time that is in between two bus stops, it's not necessarily the same time. So it's just progressing in terms of time events. And then it can be time triggered somehow, or it can be event triggered. And then you are just counting events with this k plus 1, k plus 2, and so on. So in principle, it's not necessarily like constantly progressing. Of course, a special case is that whenever you are continuously progressing with a constant rate, yes.
Okay, there are no questions from the remote audience, so a few details. Oh, there's a question.
Sorry, I want to try to make an intervention. My undergraduate background maybe didn't allow me to understand all of the talk, but I want to take an higher level understanding.
Yeah.
Am I right if I say if control theory is a way to simplify the development of, I don't know if we recall the example, the plane-based example, a way to simplify computation and delegate the more complex decision making to control theory?
Yeah, so the question is it true that control theory can be used as a tool for simplifying the design of some complex functionality, and then we can delegate this sort of decisions to control algorithms? The answer is yes and no. So the point is control algorithms are simple to use whenever you know how to use them. So that's the tricky part. But then when you know how to use them, and when it's just a matter of implementing them, they are extremely simple and efficient in the way they are behaving. And then the type of decision, it's up to you to design. So it can be like a very simple decision, like maybe tweaking a bit the how you are measuring time, for example, in the clock synchronization case. Or it can be a bit more complex decision that is like maybe you have several different actuators, like several different resources. Maybe you have number of cores, memory, frequency, and several different things, and you don't really know where to start. Then there are some tools like MPC that can be used for sort of trading off or trying to use many different things at the same time. and then simplifying a bit the overall design. Yes. One thing that I would like to mention is that one interesting fact by using, let's say, this control-based approach is that from the outside, if you sort of put a black box around the controlled system, the type of behavior that you are going to experience is going to be extremely predictable. Like, for example, if you think about the air conditioning system. So you don't know how it works. You have no idea. You just say, I would like to get 20 degrees now in my room. And then something magical happens. And then you get 20 degrees within a certain amount of time. And I even can tell you how much time it will take to get to 20 degrees. So that's the type of things that you can do with control that maybe using other approaches may be a bit more challenging to guarantee, for example, or to sort of get the same predictability in behavior. Did I respond to your question? Okay. Maybe we can talk even more.
I had a follow-up question, but actually there is someone from the remote audience. Kushal, if you can open your mic and ask your question. It's the last one of the session.
Hi, thanks. Thanks for the talk, Alessandro. It is very interesting. I have one question that is regarding, well, I wanted your opinion on this. How do you think control systems are deal with situations where you have uncertainties, in the sense that maybe you are not able to predict the kind of IoT devices that would be in your network, or maybe you cannot predict the kind of behavior that they have. It's not non-deterministic, for instance.
Yeah, that's a very good question, and the point is that several times control systems are designed having uncertainty in mind, because, for example, going back to the usual examples of, for example, controlling the temperature in the room, you have no idea how many people will be in the room, if the doors are going to be open or closed, if the windows are going to be open or closed, and so on and so forth. So there is a lot of uncertainty behind the environment that you cannot really control, and that you have no idea how, or you may have some idea of how they are going to affect your system. And then in principle, the idea of control is that by design, you are going to deal with this uncertainty in a way that you are trying to reject the behavior of undesired, let's say, components or unexpected behaviors of some of these components. So somehow it's inherent in the design process of control systems that you are taking into account this type of domains. And then, of course, if you can measure some of this uncertainty, then you can counteract this uncertainty even better. But several times you cannot do that. Like, for example, even the wind in a car. So you cannot really use the information about how fast the wind is coming against you for controlling the speed of a car. You just like speed up a bit more and then you reach your goals. Something like that. Did I respond to your question?
Yes, got it. Thank you.
Okay, let's thank our speaker again. The technical part of the conference will be we'll start at 3:30, and a few details on the social part that begins now. Off the room, on the left-hand side, there's the bar. There's a coffee break, which is free for the participants. You can get there. There should be a ticket or something that you can get for having your coffee at the bar. Plus, there is stuff that you can eat, whatever. After Luca's talk, there will be a hybrid social event. So there will be a participation from both you in the room and those who are following remotely. To play, it's a simple game. And to play the game, you will need a cell phone. I hope you have a smartphone. After that, if everything goes correctly, there should be a bus outside the campus waiting for us. I've got a list of the people that let's say achieved the honor to join the bus. It's 54 places, and some people wrote me today or yesterday that they're not gonna make it. So you should have your badge in the back side of your badge. There's a number. I will call people on the bus, basically in that order, till the bus is filled up. It's quite possible that we can fill all of those that won't come. We will move to Misano. There will be a cat race. Then we take the bus again. That will leave us to the Scottadito. At runtime, I will ask the driver if he's okay with dropping some of us at the campus if someone has the car. But this, I mean, I didn't think about it before, so I don't know if the guy is okay with that. Also because we paid it already, so I cannot just, okay, I'm gonna pay you more. And then there will be the social dinner. Then, I mean, then go to sleep because it's okay. go to the bar, go to the bar and enjoy the coffee break, and see you in 25 minutes.